Hello and welcome to Pre-Calculus 20. Today we'll be looking at sequences and series. This is chapter 1, specifically today 1.1, which is arithmetic sequences. Now in your handout you have a page that looks like this where it has a warm-up. This I'm going to leave for you to do on your own, so follow through these. I've scratched this from the handout, so don't bother with that one. But go ahead and complete these. They're fairly straightforward and simple. We will be referring back to these later in the lesson. So, I'm going to start the lesson right here. Sequences. An ordered list of objects, elements, or numbers is referred to as a sequence. The numbers that make up the sequence and follow a pattern or rule to determine the next are referred to as terms. So there are a number of terms in every sequence. The first term in a sequence is always referred to as T1. Hard to imagine why they call it that. I don't get it. The number of terms in the sequence is referred to as N. The general term of the sequence is referred to as Tn. So this is T to whatever number you're looking for. This term is dependent on the value of n, obviously. Alright. So the two types of sequences we want to talk about today. We have finite sequences and infinite sequences. Now, you all know what infinite means, goes on forever. Finite is just the opposite of that. It doesn't go on forever. So, it has to terminate at some point. So here's an example of one. Now, if we look at this thing, we start at 3, we jump to 7, then we jump to 11, and we have blank blank, we don't know, whatever. Right away you can see there's a jump of 4, there's a jump of 4 again. So that's going to be our common difference in our arithmetic sequence here. So we'll have another jump of 4, which puts us at 15, another jump of 4, which puts us at 19, and then you can see that obviously if we continue with that pattern of jumping by 4s, we go to 23, and then to 27, and here we have a period at the end indicating that this is where we're stopping our arithmetic sequence, and that is what makes it finite, is that we do stop. An infinite sequence has an infinite number of terms. It'll go on forever. So we just write the general term and then we throw ellipses at the end to indicate that it's going to keep going. So here's an example. 8, 13, 18. So here we have a common difference of 5, and again a common difference of 5. So our sequence is going to continue in that manner. So we will next have 23, and then 23 plus 5 is 28. And you could keep doing this. So in an infinite series, each term is always followed by a new term. There's nowhere to stop. It never ends. So, arithmetic sequences. A sequence of numbers in which the difference between consecutive terms is constant. This is referred to as an arithmetic sequence. Okay, we will differentiate this between another type of sequence we're going to look at later. In other words, the same value or variable is added to each consecutive term to create the next term. Now, when I say added here, our common difference could be a negative number, in which case if we're adding a negative number, it will appear to be a subtraction. So you can have arithmetic sequences that actually go down as you move along. The constant that is added to each term is called the common difference. It is represented by the variable d. Why would they use d for difference? I don't get it. The value of the common difference may be determined by taking any term in the sequence and subtracting the one that precedes it. So, if we wanted to find the common difference, we take any term in the sequence, subtract the one before it. So 28 minus 23, and we find the common difference is 5. Okay? 27 minus 23, common difference is 4. That will work for any term. So you take 1, subtract the 1 just before it, and there's your difference. Number 5 says refer to the warm-up questions from number 1. This I'm leaving you to do on your own, so I'm going to skip that. You can show me in class tomorrow. So, number 6, refer to this arithmetic sequence. 5, 10, 15, 20, 25, 30, 35. Okay, this is a fairly straightforward sequence. What is the value of all of these things? T1, that is the first term always. First term is 5 right there. T2, second term, 10. T3, third term, 15. T8, 1, 2, 3, 4, 5, 6, 7. Doesn't go up to 8, but we know the common difference. It's jumping by 5 every time. So obviously we can take T7 and add 5 again and get T8, which will put us at 40. Now this one's a little trickier. T20. We could keep going and count on our fingers all the way up to T20, but probably don't want to do that. So we can use a little trick. Now here, you might notice that T1 is 5, T2 is 5 plus 5. So 5 plus 5 times 1. T3 is 5 plus 5 times 2, or 5 plus 10. Okay? Now, notice that, well, T1 would be 5 plus 5 times 0. Sorry, I'm kind of crowding everything in here. Notice that this 5 plus 5 stays constant, and we're always multiplying by 1 less than the term number. Okay? So if we want to find any general term, like Tn, we could take 5, which is term 1, add 5, which is our common difference, and then multiply it by not n, but 1 less than n. So term 3 we're multiplying by 2. Term 2 we're multiplying by 1. Term 1 we're multiplying by 0. So Tn, term n, we're multiplying by 1 less than n. Okay, now this is actually the answer for F, but it will help us figure out T20 without having to do all that counting. We could do this really quickly. T20 would be, we can use our general term now. T20 would be 5 plus 20 minus 1, which is 19 times 5. Okay, 19 times 5 is 95, and then we add 5 and we get 100, which is your answer for T20. Okay. So developing the general term Tn, which we did just up there, if we use T1 as our first term and D as our common difference, we can write out the general arithmetic sequence as follows. T1 plus 0 times D. T1 plus 1 times D. T1 plus 2 times D. T1 plus 3 times D. Okay, this will continue all the way up to here until we get T1 plus n minus 1 times D, where again, T1 is your first term, D is your common difference. These are very easy to identify in any arithmetic sequence. Thus, to find the nth general term of a sequence, we can use this formula. Tn equals T1 plus n minus 1 times D, where the first term of the sequence is T1, The number of terms is n, and the common difference is d. There you have it. Here's an example. A visual and performing arts group wants to hire a community events leader. The person will be paid $12 for the first hour of work, $19 for 2 hours of work, $26 for 3 hours of work, and so on. So, write the general term that you could use to determine the pay for any number of hours worked. What will the person get paid for 6 hours of work? So let's start with question A here. Now, we're going to identify a few things here. T1 is $12. That's the first term. 1 hour of work will net that person $12. Now, the next hour, that person is going to make $7 more than the previous hour. Okay? So T2 equals 12 plus 7. T3 equals 12 plus 7 times 2. Because again, you're going from 12 to 19, which is 7 once, and then we're going from 19 to 26, which is 7 twice. Okay? So the general term that you could use then is going to be T1 plus, we know T1, so why don't we just write it in there? So T1 is 12, so we're going to use 12 plus 7 times, let's call it H, for hours, number of hours worked. What will the person get paid for 6 hours of work? So now that we have a general term, all we have to do is take that term and plug in the number 6. Okay, so right there, 6 hours of work, and that will yield 7 times 6, which is $42. So $12 plus 42, and then that will net $54 for that person. Okay, so here's your turn. I want you to go ahead and try this, and when you come back, I'll have the answers ready for you up on the screen. So when I indicate, I want you to just hit pause, try to complete this question, then when you're done, unpause it and you can check the answers. Okay? So go ahead and hit pause now. Welcome back. That's assuming you actually bothered to hit pause and attempt the question. There's your answers, so you can hit pause and compare them with your own. Here's another example that we're going to do together. Determine the number of terms. So this time, we will be searching for the variable n. The musk ox and the caribou of northern Canada are hoofed animals that survived the Pleistocene era, which ended 10,000 years ago. So in 1955, the Banks Island musk ox population was approximately 9250. Suppose that in subsequent years, the growth of the musk ox population generated an arithmetic sequence in which the number of musk ox increased by approximately 1650 each year. How many years would it take, nice circling job, doll, would it take for the musk ox population to reach 100,000? Okay, a few key things that I've circled along the way. So the musk ox population starts at 9250. Okay, that represents T1. This is the beginning of the arithmetic sequence. It increased by approximately 1,650 each year. Okay, this is the common difference, because every year we will add that many musk ox to the population. How many years is the big question here? So that's n, and it gets a question mark. Would it take for the musk ox population to reach 100,000? So what is 100,000? Well, 100,000 is the nth term. Okay, so we want to know how long it takes to get that term to equal 100,000. So we can plug it into our formula where Tn equals T1 plus n minus 1 times d. So this looks like 100,000 equals T1, which is 9250, plus n minus 1, and we don't know n, so that has to stay as n minus 1 right there, times d, which is 1650. Alright, let's go ahead and solve this thing. So we need to work backwards. Take 100,000, subtract 9250 from each side. 100,000 minus 9250 leaves us with 90,750 equals n minus 1 times 1650. Okay, now the n minus 1 is attached to this 1650 by multiplication. We want to get the n minus 1 alone. Okay, so don't divide off n minus 1 because then it will be in a denominator and it will be paired with this thing. It'll just make more work for you. This is the one we want to divide off. So 1650 from both sides. Okay, so hit up your calculator. Divide by 1650. There you go. 55 equals n minus 1. Now to get n by itself, add 1 to both sides. N equals 56, so it will take 56 years before the muskox population reaches 100,000. Here's another your turn. Give it a try. When you come back, the answer will be there. So hit pause now. Welcome back. Here's your answer. It says 38 months. 38 months. Can't seem to move it, so there you go. One last example before we're done. Determining T1, Tn, and n. Jonathan has a part-time job at the local grocery store. Good for you, Jonathan. He has been asked to create a display of cereal boxes. Oh, isn't it just lovely? The top 6 rows of his display are shown. The number of boxes in the rows produce an arithmetic sequence. There's 16 boxes in the 3rd row from the bottom and 6 boxes in the 8th row from the bottom. How many boxes are in the bottom row? Here's an interesting one. 16 boxes in the 3rd row from the bottom. So we want to know how many are in the bottom. But we don't know D. We don't know T1. Seems like we really don't know much at all. Okay. But here we have the 3rd row and we have 16 boxes. We are also told that this is an arithmetic sequence. So 4th row, question mark, 5th row, these are rows from the bottom. 6th row, these are all question marks. But we know that the 8th row from the bottom has, 6 boxes. Okay. So here we have a split of 10 and we need to fill 4 spaces, which means we need to make 5 jumps because we have to jump from this one to this one. So 1 jump, 2 jump, 3 jump, 4 jump, and then the 5th jump down to the 6th. So we need to make 5 jumps and we need to have a difference of 10. So a difference of 10 in 5 jumps will mean we need to make 2 jumps, or a jump of 2 per jump. So this one will go from 16 to 14, 14 to 12, 12 to 10, and 10 to 8. And then you can see that it makes sense to jump by 2 every time. But this number is going down, so we are going to jump by -2. And this will be our D value. Now this will help us move forward here. So we have our D value of -2. Okay. Now our 3rd term had 16 boxes in it. That was the 3rd row from the bottom. So if we want to figure out our 1st row, our very bottom row, we just work backwards. Here we had 16 boxes, and we know that we jump by -2 every time to move on to subsequent rows. But if we wanted to work backwards, then we would do the opposite and we would just add 2 every time. And our top row would have 20 boxes. So now we have T1 equals 20, which is the answer to question A. D, our common difference is minus 2. Determine the general form Tn for the sequence. So now we can have Tn equals 20 plus n minus 1 times D, which is negative 2. What is the number of rows of boxes in his display? He's been asked to create a display. The top 6 rows are shown. Okay. So these are the top 6 rows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, rows of boxes in his display. This row has 12 boxes in it, and that means we know that it is the 5th row, which means there will be 4 rows below it. Okay, so this is row 5, then this is row 6, row 7, row 8, row 9, and row 10. And that's it. That's your answer. There will be 10 rows in his box display. Alright, so here's another your turn. Again, go ahead and give it a try. The answer will be there when you come back. Good luck. Here's your answers. Hopefully you were able to get the correct ones there. Here's another your turn. I'm going to leave it up to you to give it a try. We are going to discuss the solution in class tomorrow, so give it a try and bring your solution to class tomorrow. That's it for now. See you in class tomorrow.